Okay, great. Hi, everybody. Just give me 2 seconds to get my screen and everything set up. Okay, so you can see sliding window. Okay, excellent, excellent. I will just want to move all these Zoom controls out the way because I don't know about you, but they tend to take up a lot of space on the screen. Okay, great. Awesome. Thank you, Helen, for that super introduction. It is an absolute pleasure to be back at Women Who Code London. And it is my pleasure to bring you your last session on your algorithm track. Today we're going to be talking about the sliding window technique. So button here. Yeah, so Helen's broken it down. But yeah, quick recap. I've gone on a journey from being a full stack dev. It wasn't called full stack back then, but it is now. And moved on to backend data engineering. I've been in a couple of different domains. And I run a test-driven development and ensemble programming group through a different meetup. And if that is something that could interest you, you can find some information about that on my website, along with a couple of blogs that I occasionally get to when I have extra time. And if you want to, I'm not a massive tweeter or anything, but if you want to follow me, I'm at Sarah N. Usher. Cool beans. So today we are going to talk about the sliding window technique. And sometimes this is called an algorithm. I'm going to stick with the word technique because I feel it's just a little bit more correct in the sense that I find it's something that you apply to an algorithm rather than necessarily being an algorithm itself. But if you want information about it, if you use just sliding window or sliding window algorithm or sliding window technique, you'll find a lot of information about it. It's also a paradigm that is used beyond the problems you'll see today. It's used in protocols, it's used in data streaming, and there's lots of other places where you'll kind of see this paradigm. Just want to mention that all the code that I'm going to use in this presentation is included in a public GitHub repo, which I will be sharing. So please don't feel like you need to write the code down or anything. I will make that available during this presentation. And I assume we make the slides and stuff available as well. So yeah, let us jump into it. If I click on the thing, there we go. Okay. So as most of the problems you would have encountered in this track, this is going to be about processing a collection and hopefully optimizing the processing of that collection. When we are talking about a window, we're literally going to be talking about a view, a subset of that collection. And this window is going to be something that you slide along. I couldn't find a very nice animation for it, so my weird dance moves I'll have to do. But yeah, so it's the idea of taking this view of this collection and moving it along each element. Another word for this is subset. So you're going to be looking at a subset or a subarray of your collection. Okay. This is not a window. So just random elements across the collection are not a window. So they're always sequential and next to each other. One of the reasons you want to use this technique is it's quite useful for reducing the complexity of an existing algorithm from something higher than ON down to ON, i.e. linear. So no matter so your complexity will grow with the collection size, but not exponentially. Cool. So I like to learn by example, and we're going to go through some examples in this session. If you have any questions for me, just put them in the chat and I'll occasionally come back to the chat, but it just helps me not to break my train of thought, if that's okay. But please do let me know if you have questions, and if you want to nod at me, you can put your camera on and I will have a look at you, because That way I know that I am either losing you or not, but yeah, okay, great. So in our first example, we're going to be dealing with this collection here. And what we want to do is we want to find a subset. So that inner set of 3 items or 3 elements that have a maximum sum. Okay. So what I mean by this is we want to take 3 of these elements and add them up to create a sum. And we want to understand which grouping of 3 has the largest sum. Okay. Cool. So let's have a look at what those look like in this particular example. We've got 4 different possible inner sets, and these are the sums of those particular sets. So the obvious winner is the one that sums to 68 here. Okay, so that's what we can see just by looking at this. What I'm going to take you through now is how you might do this without windows. So I'm just going to, I think I have these in the wrong order. So let's just explain this. So here we have an algorithm. It's pretty straightforward. All you're really doing is you're going to loop through the collection once. So you're only going to need to go up to this element here, the one that has a value of 20. You don't need to go through 36 and 12 because our window is 3. So a window of 2 or a window of 1 is not a valid window in this problem. Okay. And then you will then loop through each subset again. So back here, we're going to loop through the collection again and take that set of 3 and get the sum, right? So if we loop through here once, we will start, I'm pretty sure I have other slides for this. Let me just check. Yeah, okay. So to do this, we're going to have a couple of variables. We're going to start at 0. Okay. We know that 3 is the size of the window. The convention for this number is k. So we'll say k is 3, and we're going to have another variable that keeps track of the total. Okay. Let's do that step by step. All right. So as we saw, our first set is this one here, which is 0 up until k, which is 3. Okay. And then that is 18 plus 8 plus 4, which is 30. Okay. So our next collection is going to be, I know what I've done. Okay. Sorry. I'm just going to start again here. Okay. So, right. Let's go back to the brute force algorithm. Sorry, I changed my size just before, which is a fatal flaw. So let's recap. If we just loop through the collection once here and then loop through it again, and for each time we loop through, we're going to start at I. So what I mean there is you are going to start at 0 and you're going to count 18, 8, and 4 and get 30. Then you're going to move along and you're going to start at 1, index 1, and you're going to get 8, 4, and 20. Okay, and you're going to continue that way. So let's read this. Through 0 to, this is in Python, so range does not include the last number here. So up until index 4, okay? You'll collect the total for the up to those 3. So for the first one, I, where I is 0, it's going to be 18 and then plus the next 2, 8 and 4. Okay, and you carry on this way. This is pretty straightforward. As you go through each set of 3, and you loop through your collection once, and then again here, you will check for the total. So the question was, I want the maximum total. So I want the set of 3 where I have, which has the largest sum. Okay. So there we have, and then this checks that. So every time we find a larger sum, we will set it in max total and then send that max total back. So obviously the first time it's 0 and 30 is bigger than 0. And in fact, all of these are bigger than the other. So they'll all go into the max total and eventually returning to 68. Okay. And then this, to understand the complexity of this, you know from previous sessions that looping through your collection, every time you have to loop through your collection is an n squared case. If you have to calculate this, it's probably not exactly n squared because you don't necessarily have to loop through the entire array. You do stop here and you do start partway through here, but you can summarize that up to n squared. So I just wanted to explain that because sometimes you'll see very explicit calculations of ON, and sometimes you'll see like the summarized version where someone has taken it to sort of the next obvious point. Often constants don't matter, and this is not necessarily obvious. So I just wanted to mention that. I'm going to check the chat. Okay. Sorry, I had to restart there. Did I lose anybody? Are you all with me? Emma says yes. Okay, great. Thank you, Emma. Okay, now we're going to use Windows. This paradigm of looking at this code as Windows and not just something plus K. Okay, still the same problem. So to do this, we're going to use variables to keep track of things. We're going to keep track of the start of the window. So that'll start at 0. We're going to keep track, or we have to know what K is because the window is set. So it's 3. And as I mentioned earlier, this is the convention. So when you look at other algorithms using sliding windows, they'll often use K for a set window size. And then we know that we have to keep the total, and that's the same as the brute force algorithm. Okay. So looking at our first window, what I have here in this notation is that I'm just representing where the start variable is, and I'm representing where the end of the window is, and this should be a 0 here. Okay. Anyone who noticed and was paying attention. Okay, so the first window, as we know, is these 3 elements, which add up to 30. Okay, pretty straightforward. And we're just going to now move that window along, right? So the dance move, okay, sliding window. We're now going to be at index 1, and the end of the window is going to be at index 3. But we have a running total. So we don't reset the total necessarily to all the different numbers. We already have a value in total. It's 30, right? So to calculate the new value of total, we'll say it used to be 30. It's now going to be, we're going to take out the value that's no longer in the window. So 18 is no longer in the window. And we're going to add the new value that has come into the window. Okay. So that gives you 32. And if you do some quick maths, 20 plus 4 plus 8 will also give you 32. Okay. And repeat. So sliding along. We then go to index 2 and we repeat the same process. So we bring the 32 down here. We take out 8 because it's no longer in the window. And we add 36. Okay. And then no prizes for guessing this one, I'm afraid. pretty straightforward again. It's a pattern. So our window now has moved to start at 3 and ending at 5, which then will give you 68. And these values are the same as the other sets. But the difference is that we've used this paradigm of a window to kind of adjust the way we were thinking. So previously in the brute force algorithm, we said to ourselves, okay, let us have an index of I that we keep track of, count to 3, and then count all the values, and then repeat that, loop through that. So how is this different? Well, what we didn't do is we didn't repeat through the collection again. Okay. So if we have a look here, and I've written extremely verbose notes here so that if you want to go back and read this, you can do that. Here is that total that we were talking about, starting at 0. We get the total of the first window here. So we just say loop through from 0 until 2, because range, Python range, and got up to and excluding. Okay. I've repeated this a few times because I know not everybody does stuff in Python. Right. So that'll give you total of 30. So that goes into this variable here. And then we don't have to go through the collection again. We can actually just loop through the rest of the collection and adjust the total using this mechanism that we've discovered, where we removed the value of one thing that wasn't in the window anymore and added the value of this new thing that came into the window. Okay. So for all the other elements, move the window and adjust the total. And that's what this algorithm is doing here. So here, I explicitly say we'd start off with 30 now, because that's what's in here at the start of this line of code. We still have to keep track of the max. So we know that now the max is also 30 because we set it here. And then we check the next section. Okay, so this is just the writing of everything we just went through. So we say, while I equals 3, because I will now become k, because we finished here. So we did 0, 1, 2, and we calculated that, and then we can move to the next set. So what is happening here is we'll be at 3. So we use that to minus from the total, I minus k. So 3, yeah, 3 minus 3. So we minus 3, which is 0, which is 18 here. Oh, I clicked something, sorry. Okay, and then we add the current element that we're on, 3, index of 3. So do you see that? So I'll go through that again. We've gone, total is the collection of the first 3 elements, because k is 3. Okay, that gives us 30 in our parameters, in our variables. Then we say, okay, go from range k to the length of the array, go backwards, 3 minus 3, which is 0, get rid of 18, and 3, take in 3. So that's the second window. Okay, I'm going through this very slowly so that it's very clear. So that was the window we were talking about. And here are windows 3 and 4. So it's the same thing. You've kept track of your total. So this is the one we just did. keep track of the total. So when I is now 4, because it was 3 before, now it's going to be 4, you remove 8, okay, because it's k, I minus k, 4 minus 3 is 1. Okay, right. And then adding the element 4, and that's what's happening here. Okay. Anyone lost on this particular pattern? There is a thank you very clear. Okay, great. Cool. Right. And who wants to tell me the O of this? If you write it in the chat, I'll have a look. Cool. Yeah, thank you. It is indeed O of n, because we only go through our collection. So n represents the total of the collection, the total length. We only go through it one time. We don't have to go through it any longer than that. So that is the power here of perceiving that set, not just as a random set of numbers that happen to be next to each other, but as a window of things that we're keeping track of that will then move along as the collection moves along. Okay, and it's a very, very simple tweak, but it can be really, really powerful. And it's really brought down the complexity of this. So you can imagine if you've got an incredibly large data set and you're wondering why it's getting slower and slower, you can come back and see, okay, maybe if I use this window idea, I can not have to go through my array twice, and you'll really cut down on the length of time your function is running for. Okay, cool. So the one we've discussed here is an example of what's called a fixed window, where you know what the size of the window is and it doesn't change, it's static. It's always going to be 3 in this problem. You can also get a dynamic window. So second dance move of the evening, dynamic window. Okay. I don't know if you know, those 90s dance moves where it's like the fishing rod or the shopping bag, or, you know, this is a new one. It's the dynamic window. Okay. So the idea of a dynamic window is that it will adjust, and this is for a slightly different problem. So an example problem here is finding the minimal length of a contiguous subarray of which the sum is more than s. Okay, so what does this mean? Contiguous means sequential. It's a very fancy word. I don't know why they don't just use the word sequential, but it basically means sequential, because we know that a window isn't just random elements. It's sequential elements that are next to each other, that are a subarray. And then what we're looking for is the subarray, the smallest collection of elements that will have a sum, another total, that is bigger than some given amount. Okay, so let's look at an example, what I mean by this. So here we want to find within this collection, slightly different, the minimum length, okay, the shortest length of a contiguous, i.e. sequential subarray, of which the sum is bigger than or equal to 60. So if we just use our eyeballs on this collection, we can see that there are 2 windows that suit that particular requirement. One is this one, and the other one is this one. And the clear winner here is 2. Okay, So that's the problem. So I want to know which is the smallest subset for which the sum of the values of those elements is going to be bigger than or equal to 60. Okay, that's the problem we're dealing with here. Cool. So again, we're going to start with the brute force solution where we're not really thinking about windows. And again, we have this double loop idea happening. So for every element, we will loop over the array from the location of that element and determine how many other elements are needed to reach the condition. Okay, so here we start for each element in the array. I've got some localized parameters here. You're going to loop through from where that array is. You're going to loop through the collection again, and you're going to keep a running total. And when that total reaches the condition, so i.e. bigger than or equal to 60, sorry for the bike, then we'll keep the count of the elements. So we want to know how many elements are in that set. And that's going to be 2 at the end, which we know from looking at it. And this is how we would keep track of it. So this is kind of what that looks like visualized, because I also like pictures. might have realized. Okay, so here we're going to start off with 13. This is our brute force approach. And we're going to say, is 13 bigger than or equal to 60? No, it's not. So loop within the collection again. So keep 13, but move to the next one as well. So give me 32. Is that bigger than or equal to 60? No, it isn't. And these two are actually extra here. It isn't, so add 7. That still isn't bigger than or equal to 60. Add 21. That still isn't bigger than or equal to 60. Okay, and these two are extra, not required. So that's all well and good, but we need to understand within the rest of the collection, were there any other groups that met our requirement? So the outer loop has to move to the next index, and that's what's happening here. So then again, you start off with, okay, if I have just this one, is it bigger than or equal to 60? No, it isn't. Add this one. No, it isn't. Add this one, etc., etc. Okay, and you end up looping through absolutely every element because you can't avoid doing that. Is this good? Emma? No, it's not good. It is not good. So what we want to do is we want to change our perception of the problem and try and think about how a window here, how this window idea can help us to not have to double loop and check absolutely every single element. Okay. So we'll have a couple of variables that are very similar. We will keep track of the start of the window. And here is while we keep track of the end of the window. So unlike with the fixed algorithm, the fixed window, you can't calculate the end of the window by using start plus something. So you have to keep track of it as the programmer. And then as per usual, we will keep track of the sum, and we will keep track of our ultimate end condition, which is the lowest count of elements from the collection that satisfy the condition S. Okay. Just going to stop here and see if there are any questions before we go on. Change my zoom to the gallery just in case. Okay. Cool, 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 cool. Next. Okay, so we're going to step through this again, and we're going to visually understand how to use Windows first. Okay. So it makes sense to start with the smallest window, because ultimately the smallest window we could have is 1. You can have an edge case, of course, where none of your set satisfy the condition, and then you technically have 0. I don't have an example of that edge case in the presentation, but it is in the code if you want to have a look at that afterwards. Not really covering edge cases. I'm sure you can think about edge cases for yourself, and then when you do the practice as well. Okay, so we're going to start at 0, and we have to keep track of the end. So the end is also around 0th element. Okay, and the sum of that is 13, which clearly does not satisfy our condition. If you keep track of the minimum element, I've just used the length of the array +1, because obviously if that is the result at the end, it means I haven't found anything, and I know that I have a non-result. Other people use maximum index number or whatever it is. What you want to set in this is just something that is bigger than the largest possible solution. And the largest possible solution is, what would be the number of the largest possible solution? The count. 6. Yeah. 1, 2, 3, 4, 5, 6. Okay. Great. Yes, exactly. The count of elements in the array. Perfect. So because this does not satisfy, I'm going to expand the window. So this window is dynamic. It opens up. Okay. So then we move the end to 1. Okay. And then we sum up this 32 and 13, which gives us 45, which still does not meet the condition. So what do? We open up the window one more, and we say end is now at 2. You have to keep track of that as the programmer. The end is now at 2. This also does not satisfy.
Excuse me, Mr. Sarah.
Yeah.
Just I want to, if you want, just read the last example because I didn't understand it.
Okay. Sure.
I'm so sorry for this.
No, it's okay. Back here. Okay.
Thanks much. Thanks.
Okay, I'll start from here again. No problem. So we are keeping track of 4 things: the beginning and end of the window, the total sum of the value of the elements within that window, and the minimum current count. Okay, which we've set to higher than the possible maximum, which is the entire collection. Okay. Then what we do, because this does not satisfy the condition, we open the window further and we say, give me the next element. Sorry if you hear my cat, it's close to dinner time. We still do not have the condition satisfied, right? So 32 plus 13 is still not bigger than or equal to 60. So we open the window again, and then we keep track of where that window has been opened to, which is now index number 2. Okay. But 13, 32, and 7 still do not satisfy the condition. So what do we do next? What's the next step?
Thanks much. It's okay. I asked. Thanks much.
Yeah, no problem. I'm asking everybody in general. So Denise says we increase the end. Yes. We increase the end. We open the window further, and then we say, okay, 13, 32, and 7, and 21 does satisfy the condition. Okay. So now we can say, now that my condition is satisfied, I'm going to adjust the minimum count of elements. And that gives us, we've got 1, 2, 3, 4, and 4 is less than 7. So now we set the variable of minimum count of elements to 4. So we have our first winner, our first winning window. Who wants to guess what changes next? Yes, Emma, great. So now we keep the end where it was. So because our goal is to find the minimum window, we are going to kind of slink the first one forward until it meets the condition, and then we're going to slink the back of the window, the start of the window, closer to that, because that will give us a minimum window, because ultimately that's the problem we're trying to solve. Okay, so here we have 32, 7, and 21. And that also satisfies the condition. So because it satisfies the condition, we will test against our current value of minimum, which we know is 4, and 3 is less than 4. So that will overwrite that. And we now have a new count, which is 3. Okay. So what's happened here is when we didn't satisfy the condition, we kept moving the end. And when we did satisfy the condition, we kept moving the start. Okay. So because we satisfied the condition, we've moved the start. Then we have 7 and 21. And unfortunately, that does not satisfy the condition. So all together now, I've just repeated the next line. This line here, this is a repeat to help follow. We expanded the end. Okay. Great. So that gives us a new set of elements whose values sum together and are bigger than or equal to 60. But it's a count we already know about. 3 is 3, so that doesn't actually change. Okay. And because we satisfy the condition, it's very monotonous, but this is algorithms. Right? So we're trying to identify a pattern, and we know that the pattern here is moving the start of the window. Exactly, Denise. The start is changed again. Perfect. Very good. So now, because this satisfies the condition, what do we do? What is the next?
We can try to use just one element that is to the right. And if it does not satisfy the condition, then the minimum count of elements is 2.
Yes, exactly. So here we, following the pattern from the previous step, we saw that it satisfies, and we know that when something satisfies the condition, the next step is that we move the start. Okay. And because we've moved the start, then we check the value of that new window, and that does satisfy the condition. But the next step is actually to understand if our minimum count is updated. So there's one step that happens after we don't satisfy the result. Yeah, we check the minimum count. Exactly, Denise. So there's one step that happens after we don't satisfy the condition, but there are 2 steps that happen when we do satisfy the condition. Step 1 here is checking the minimum count. And then step 2 is moving the start closer. So what is the new minimum sum? But Anna's saying 2. Excellent. 2, because 2 is less than 3. Okay. Now I've done the same thing where I've repeated the bottom line here. I just thought this would be easier to follow. Okay, so by now you're getting tired of me saying this because you know what's going to happen, right? Here, there is what you were saying before, which is when we're now going to check 1, because step 2 of post satisfying the condition is to move the start, and that brings our end and start together, but they do not satisfy the condition because 45 is not bigger than or equal to 60, and hence we move to the end. Okay, so what we've identified here is, okay, one more slide. So let's repeat, line 19 will ultimately test the final number that doesn't satisfy the condition, and that's it, the window is closed. Okay, it's over, it's over. Aren't we glad that computers do this and not us? Okay, so here I've not copy and pasted all of them, but just some of them so that we can identify that pattern that we were talking about. So here we started at the beginning. We saw that this did not satisfy the condition. We moved the window. We saw it, the end of the window. We saw it did not satisfy the condition. We moved the end of the window. It did not satisfy the condition. We moved the end of the window. It does satisfy the condition. We check the minimum count. And we move the start of the window. Okay. So who needs me to repeat the process? I'm just joking. I know you would kill me through Zoom. It would happen. Okay. So yeah, that's just me explaining everything I just explained. Okay. The last thing I wanted to mention here is this extra step kind of just magically happens. And this is, if you break down your algorithm like this and you see something like this, it's kind of a hint that this is not necessarily a condition that will happen within the algorithm, but it is probably a function that is external. Okay, so what I mean by that is, here is the algorithm, and here is that function. Okay, so let's have a look at this and let's understand how we took that pattern and coded it, because those are two different things. So here are the variables that we spoke about, keeping track of the smallest element. Here we set it to 7. Keeping track of your local calculation of the window, starts at 0, of course. The window will start at 0, of course. And if you noticed, the end element is the first one to grow. Do you see? It is not start that increases, but it is end. So end becomes the variable that represents the loop here, the first loop. Does that make sense? Do you see how we've chosen end as the loop here, not start? Okay. So as monotonous as it is to go through this, when you've established a pattern, you can use that pattern to understand how to design the actual algorithm. Because when we brute forced it, it was like, oh yeah, obviously it's, you start at the start, right? But when you're trying to optimize algorithms, the obvious solution is generally not optimal. So we want to find a different pattern in the data. Okay. So here is where we loop over that in value that we saw. Here is where we check that we're meeting the condition. And this is a while loop, because we know that while we meet the condition, we increase which variable? Start. Okay, excellent. I repeated it enough. Okay, so here is that happening here. Start is increasing. Okay, and here are the other two things. So we meet the condition, we check. Here's that function. So this is an external function that says, is A bigger than B, or is B bigger than A, and returns whichever one is, smaller, whichever one is smaller. Okay, but it's external, which you would have covered, I believe, in your dynamic programming, where you broke up problems into smaller problems. So check if the element count is less than the current count that we do here. Then reduce the running sum. So that's that pattern here. Same as the other window, where we keep actually a running total, and we're not trying to keep a window and sum across the entire window, which would require additional looping. So that's happening here. And then because we're using the start variable's value, we change it at the end. If we changed it before, it would not grab the right values here. Okay. Oh, so that makes sense. How we discovered the pattern of this particular algorithm. I don't know. Does anybody have any questions? Yeah, sort of. Okay. So what I would suggest is practicing this. And because this is not obvious. There are definitely geniuses in the world who will read that problem and go, oh yes, but they're geniuses because they've done this kind of problem 100 million times. So the mechanism of trying to understand a small example and looking for a pattern in that example is a very useful way of coming up with the actual algorithm. And you can see here how this idea of a window, it's not something you used to store values in. It's not something that you said, okay, I'm going to physically keep an array of so many elements and I'm going to physically move this along. You didn't use it as a storage mechanism. You used it as a paradigm, a way of looking at the problem. Okay. Right. So that is the end of the examples. And now I'm going to just quickly run through how would you identify this in the wild. So you'll notice that we used a couple of words, and these are these words such as subset, sequence, subarray, contiguous are usually big giveaways that a window could be a potential solution here. Also, the use of the value k is a classic giveaway that this is probably a fixed window problem. If you identify that you might need permutations that are in a sequence, that can also give away this problem. But often when you can look at a problem and you can envision a brute force solution, or that brute force solution becomes quite naturally, or and it's fairly obvious, that's also often a sign that we don't really want to be going in that direction, and we can probably use this idea of a window, this paradigm of a window. Okay. Couple of things to note when you start practicing this, which we will do at the end of this, is your window cannot move backwards. So as you saw, as we were moving our window along, we never moved the start forward and then back again. And we also didn't do that with the end. So your window can only ever move forwards. you can write an algorithm that moves the window, but it's probably not going to be optimal because you're covering ground you've already covered. You may, in some problems, find that part of the solution isn't just a window, but is also requires you to order your solution. So that's just something to keep in mind. And as these problems get harder, they will add additional constraints. So the way to deal with constraints, sometimes I like to deal with them, is remove them initially, figure something out, and then try and put each constraint back. But that's just my preference. And as with anything in real life, are you going to really iterate over an ARB collection of numbers? Probably not. So a couple of places that you might see this being used is, it should be fairly obvious that this would be a solution for a large collection, right? And looping over a large collection, as we know, increases, can increase dramatically with time if you have a suboptimal algorithm. So one place to do that is if you've got a large collection. So if a large set of transactions or events, count of events and stuff like that, but a lot of them, aggregation. You could have quite a large set of things to process. So sliding window, very good there. I've seen people use this as a way to implement rate limiting. So if you Google rate limiting sliding window, you'll see some solutions, and real-time analytics. So this idea of a window, if you are working on a streaming data platform where you work with streams, you will probably have come across a tool that allows you to keep a running total over a subset, while that stream continues to move. And it's exactly the same principle as we've coded here, where you can keep that stream moving, but you're only looking at a portion of it at a time. Right, so these are the exercises. I'll send the link now. I assume we'll go into groups, or you can choose to do it on your own, whichever works for you. But give it a bash and approach this in a way that works for you. So if you find that the solution is obvious and you want to code it up. If you want to try with a small example and let the pattern speak to you, I found that quite effective. Give that a try. And if you want to go through the examples we went through in this presentation, the link is here. So I'll put this in the chat now. But I've written this with tests. So you'll be able to run each test for each example, and you can step through it. I found it quite useful to do that. So I've made that available as well. And I think, yeah, that's it. So I will try and find my screen share. Okay. Right. So that was a little bit long, but hopefully going through the examples was useful.
It certainly was. Thank you very much, Sarah. I'm going to stop the recording.